Some of the most trusted safety certifications in aviation history were signed off without testing the one failure mode that caused 80% of documented incidents. 22 different seat track models, used across dozens of airlines, certified by engineers who knew exactly what they were doing, and not one of them was put through the specific loading condition that would later cause seats to rip out of the floor mid-flight. This is not about a mistake. This is about the gap between what certification required and what physics actually demanded. Some of these approvals will make perfect sense when you understand the regulations at the time, and a few of them will make you wonder how anyone thought it was acceptable. Number 18 involved a test that simulated forward loads but completely ignored the twisting motion that happened in every real-world accident. Keep watching. The original single-pin seat track attachment. These defined commercial aviation seating from the 1950s through the early 70s. One locking pin per seat leg. Simple, lightweight, easy to reconfigure the cabin when airlines wanted to change seat layouts. The entire seat row locked into a floor track with pins that dropped into pre-drilled holes. In a sudden deceleration, those pins were designed to handle forward loads. Straight ahead. Engine failure on takeoff, hard braking, that kind of thing. What they were never tested for was the combined twisting and upward motion that happened during turbulence or asymmetric impact. When the aircraft pitched or rolled suddenly, seats did not just push forward, they lifted and twisted simultaneously. That single pin became a fulcrum. The seat would lever upward, the pin would shear, and the entire row would break free. Passengers in those seats had no structural attachment to the aircraft anymore. They became projectiles. The FAA did not require multi-axis loading tests until after a series of incidents in the early 70s where seats detached during severe turbulence and slid into other rows. The new standard required dual-pin attachments with redundant locking mechanisms and testing that simulated pitch, roll, and yaw simultaneously. What was lost here was not romance. It was convenience. Airlines could reconfigure cabins in under an hour with those old single-pin tracks. Modern dual-locking systems take longer to install and remove, but a seat that stays attached to the floor is worth the inconvenience. The certification engineers were not incompetent. They were working with standards that had not yet caught up to observed failure modes, and passengers paid for that gap with injuries that should never have happened. The flush mount track design used in regional aircraft through the 1980s. These were beautiful from an engineering standpoint. The seat track sat completely flush with the cabin floor, no raised rails, no trip hazards. Passengers could walk the aisle without watching their feet. The track was recessed into the floor structure and the seat legs dropped into it with a spring-loaded locking tab. Clean, elegant, tested extensively for static loads, certified without a single dynamic impact test. Static load testing means you bolt the seat down, hang weights on it, and see if it holds. You are testing the strength of the materials. You are not testing what happens when that load arrives in a fraction of a second during an actual crash. During a survivable crash, the deceleration is not smooth. It is a spike. The seat experiences a sudden shock load that can be 5 or 6 times higher than the static weight would suggest. Those flush tracks were strong enough to hold the rated load indefinitely if you applied it slowly. They were not strong enough to handle the shock transfer that happened in a real accident. The locking tabs would deform. The seat would pop out of the track. Entire rows came loose in accidents that passengers walked away from otherwise. The updated certification standard required dynamic impact testing. You mount the seat on a sled, accelerate it to realistic crash speeds, then stop it suddenly and measure what happens. Tracks that passed static testing failed dynamic testing immediately. The new designs required deeper engagement, hardened locking mechanisms, and secondary retention clips. What was lost was the clean cabin floor. Modern tracks are raised or require reinforced floor panels that add weight and complexity. The flush mount aesthetic was genuinely better for passengers. And it was certified based on tests that had nothing to do with how seats actually failed. The quick-release lever mechanism certified in the 1990s for business jet seating. This was premium engineering. Passengers could reconfigure their own cabin. Want to turn your seat to face the conference table? Pull the lever. Want to slide it backward for more legroom? Pull the lever. The seat rode on a track with a spring-loaded lever on the side that you squeezed to unlock. It was certified under the existing standards for business aviation, which were less stringent than commercial transport standards. The testing focused on whether the seat could be locked securely once positioned. It did not focus on whether that lever could be accidentally released during an impact. In a crash, your body moves forward. Your hand, if it is near that lever, also moves forward. If you are gripping the armrest and that lever is right there, you can pull it during the deceleration without meaning to. The seat unlocks mid-crash. Now you are sliding forward on the track with no restraint except your seatbelt, which is attached to the seat that is now moving. Multiple accidents in business jets involved seats that became unlatched during the impact sequence. Passengers ended up several feet forward of where they started. Some hit the bulkhead, some hit other seats. The mechanism worked exactly as designed. It was just never designed assuming someone would grab it during a crash. The updated standard required lever guards and secondary locks that could not be released under load. Business jet cabins lost some of their flexibility. You cannot casually reconfigure the seats mid-flight anymore on most models, and passengers stopped sliding into bulkheads because they accidentally unlocked their own seat during an emergency. The certification process assumed intentional use only. Physics does not care about intention. The lightweight composite track used in regional turboprops in the early 2000s. This was cutting-edge materials engineering. Composite materials instead of steel, 40% weight reduction compared to traditional tracks, fuel savings across the fleet, tested for tensile strength, corrosion resistance, fatigue life, certified for use in aircraft with fewer than 20 seats under Part 23 regulations. Never tested for the specific case of a seat track pulling up and out of the floor rather than pulling forward along it. Composite materials are incredibly strong along the fiber direction. If you pull them the way the fibers run, they hold massive loads. If you pull them at an angle across the fibers, they delaminate, layers separate, strength drops catastrophically. In forward impacts, these tracks performed beautifully. In accidents involving significant vertical or lateral forces, the tracks would peel up from the mounting points. The composite would delaminate where the bolts attached it to the floor. Seats stayed locked into the track. The track came out of the floor. Same outcome, different failure mode. The FAA eventually required peel testing for composite seat tracks. You mount the track, then apply force at an angle designed to lift it away from the floor, and measure how much force it takes to fail. The original composite tracks failed peel tests at loads well below what could occur in a survivable accident. New designs required additional layers, different fiber orientations, and metal reinforcement at the attachment points. Weight savings dropped from 40% to about 15%, still better than steel but not the revolution it was marketed as. What was lost was the promise of radically lighter aircraft. What was gained was seats that stayed attached when the aircraft did not land perfectly level. The engineers who designed these were not cutting corners. They were working with certification standards that tested strength but not failure mode. If you are the kind of person who wants to know not just what regulations exist, but why they were written the way they were, I have put together a breakdown of every major aviation seat certification standard, the accidents that drove each change, and the specific test requirements that replaced the old ones. It is organized by decade with the actual failure modes described in engineering terms. Grab it at the link in the description. The side-facing seat configuration, certified for military transport aircraft and later adopted by some charter operators. These were standard in cargo planes that occasionally carried passengers. Seats mounted along the fuselage wall, passengers facing the center of the aircraft. Efficient use of space. You could fit more people in the same fuselage volume. Certified under military specifications that prioritized loading flexibility over crash survivability. The problem was not the seat itself, it was the direction of force during a crash. In a forward-facing seat, your seatbelt restrains you against the primary direction of deceleration. The belt is oriented correctly. Your body wants to go forward, the belt stops you from going forward. Physics is aligned with the restraint system. In a side-facing seat, during a frontal impact, your body wants to go forward but you are sitting sideways. The lap belt is now trying to restrain lateral motion it was not designed for. Your torso rotates. Your head whips to the side. The loading on your spine is completely different. Military passengers were typically young, healthy, and briefed on crash positions. Charter passengers were not. Several accidents in the 1990s involved charter flights with side-facing seats where passengers sustained spinal injuries in otherwise survivable crashes. The forces were not extreme. The direction was just wrong for the restraint system. Civilian certification standards eventually prohibited side-facing seats in commercial passenger operations unless they met the same dynamic testing standards as forward-facing seats. Almost no side-facing designs could meet that standard. The restraint geometry does not work. Military transports still use them because the operational requirements are different, and the risk is considered acceptable in that context. Charter operators lost the ability to pack more passengers into cargo-configured aircraft, and passengers stopped experiencing spinal loading that their seatbelts were not oriented to prevent. The seats were tested. They were certified. The tests just did not account for what happens to the human body when the direction of restraint does not match the direction of crash forces. The spring-loaded folding jump seats certified for cabin crew use in narrow-body aircraft. These were genius from a space-saving perspective. Crew sits down, seat drops from the wall. Crew stands up, seat folds back up flush with the bulkhead. No floor space used, easy to get out of the way during boarding. Certified under standards that required the seat to restrain the occupant during normal turbulence and during a survivable crash. What those standards did not specify was how the seat should behave if the occupant was not fully seated when the crash began. If the crew member was in the process of sitting down or standing up and the impact happened, the seat could fold up mid-crash. The spring mechanism that made it convenient to stow also made it easy to collapse under unexpected load. Several incidents involved cabin crew being thrown from jump seats that folded during impact because they were not fully seated when the deceleration started. The seat did not fail. It did exactly what it was designed to do. It folded when there was not enough weight on it to keep it down. The problem was that during an emergency, crew are moving. They are not always seated at the moment of impact. Updated standards required jump seats to have a positive lock that prevented folding once deployed and required the lock to be engaged before the seat could be considered occupied. Modern jump seats do not fold up until you manually release them. They are heavier, they are slightly less convenient, and they do not collapse out from under crew members who are trying to sit down during an emergency. The certification tested the seat with a seated dummy. It did not test what happened if the dummy was half standing when the sled hit the wall. Engineers cannot test every possible condition, but once a failure mode is observed, it becomes inexcusable not to test for it. These seats were certified by engineers who followed the standards exactly. The standards were incomplete. The original three-point belt system certified for use with non-reinforced seat backs in commuter aircraft. This one is subtle. The three-point belt itself is one of the great safety inventions in history. Lap belt plus shoulder belt, it works. What made this dangerous was where the shoulder belt was attached. In a car, the shoulder belt attaches to the body of the vehicle, strong mounting point. In some early aircraft seats, the shoulder belt attached to the top of your own seat back. Your seat was holding you in place. As long as the seat back was strong enough, this worked. Early certification standards required seat backs to withstand a certain amount of rearward force. Enough to handle a passenger pushing back into the seat during normal flight, not enough to handle the force of the person behind you slamming into your seat back during a crash. If the aircraft decelerated hard, the passenger behind you would load into the back of your seat. Your seat back, which your shoulder belt was attached to, would collapse rearward. Now your shoulder restraint is slack. You are restrained only by the lap belt. Your torso goes forward, your head goes forward. Injuries that the shoulder belt was supposed to prevent happen anyway because the shoulder belt is attached to a structure that just failed. This was observed in multiple commuter aircraft accidents in the 80s. Passengers in seats with three-point belts still sustained head and chest injuries because their seat backs collapsed under loading from the row behind. The updated standard required seat backs to handle a much higher rearward load and required dynamic testing with a dummy in the row behind to simulate that impact. Seats that passed the original standard failed the updated one immediately. New seat backs required reinforced frames and different mounting geometry. What was lost was light, simple seat construction. Modern seat backs are heavier and more expensive to build. And passengers in the forward row stopped having their restraint system go slack mid-crash because the seat back was not strong enough to do the job the shoulder belt relied on it to do. The three-point belt was certified. The attachment point was certified. The system failed anyway because the two certifications did not test the interaction between them. The aluminum floor track extrusion used across multiple aircraft types in the 70s and 80s. This was an industry standard design. Extruded aluminum with a specific cross-section that the seat legs locked into. Strong, lightweight, easy to manufacture, certified based on the strength of the aluminum itself and the geometry of the locking interface. What the certification did not account for was what happened to aluminum under repeated stress cycles over years of operation. Aluminum work hardens, then it fatigues, cracks develop at stress points. In a floor track, those stress points are where the seat locks into the track. Every time someone sits down, every time the aircraft lands, every time there is turbulence, the track experiences a loading cycle. Over years, microcracks form. The track still looks fine, it still holds the rated load in a static test, but its ability to handle sudden impact has degraded. Multiple accidents in the 80s and 90s involved seat tracks that had been in service for years. The seats pulled out of tracks that had passed inspection. Post-accident analysis found fatigue cracks in the track material around the locking points. The track had been certified for the strength of new aluminum. It had not been certified for the strength of aluminum after 10,000 loading cycles. Modern standards require fatigue testing. You mount the seat, cycle it through thousands of simulated loading events, then test it for crash loads. Tracks that look identical when new perform very differently after realistic service life. Older aircraft had to have floor tracks replaced on a schedule based not on visible wear but on cycle count. Airlines lost the assumption that a part that looked fine was still safe, and passengers stopped sitting on seats that were attached to floor tracks that had been quietly failing for years. The aluminum was strong. The certification proved it. The certification just did not prove it would stay strong after years of use. Engineers who certified this were not negligent. The concept of fatigue testing for cabin components was not standard practice yet. It became standard after people got hurt. The original armrest-mounted in-flight entertainment systems certified in the late 90s. Brilliant design at the time. Flip-up screen in the armrest. Watch a movie without a seatback screen taking up space. Lighter than seatback systems. More design flexibility for the aircraft interior. certified as a seat component under existing standards that required the seat to handle crash loads. What was not considered carefully enough was what that heavy screen in the armrest would do during a crash. In a side impact or during turbulence, that armrest with a screen mounted in it became a swinging hazard. It was hinged, it could flip up. Now you have a multi-pound object on a hinge right next to the passenger in the next seat. In several turbulence events, passengers sustained injuries from armrest-mounted equipment that came loose or struck them as they were thrown sideways. The armrest itself was certified. The mounting was certified. What was not tested was the dynamic behavior of a hinged mass during lateral acceleration. Updated standards required any armrest-mounted equipment above a certain weight to have positive latching and to be tested for side impact scenarios. Most armrest entertainment systems were phased out not because they failed testing, but because seatback systems became lighter and cheaper. But for a period of about 10 years, you had certified equipment that could hit you in the ribs during turbulence because the certification tested forward loads and ignored lateral ones. What was lost was a genuinely clever design solution. What was gained was not getting hit by your own armrest. The engineers who put screens in armrests were innovating. The standards they certified against were written before anyone thought to put heavy electronics on a hinge next to passengers. The friction lock recline mechanism used in economy seating through the 2000s. You have used these. Push the button, lean back, the seat reclines and stays there. The mechanism is a friction lock. Spring pressure holds the seat back in place. It works perfectly under normal conditions. The problem was what happened during a crash. If the passenger behind you was not wearing their seatbelt, or if their belt failed, they would load into the back of your seat during deceleration. That friction lock was designed to hold the weight of a reclining passenger. It was not designed to hold the impact load of an entire human body slamming into it at crash speeds. The seatback would collapse forward. Your seat would go from reclined to fully upright to past upright, dumping you forward and down. The passenger behind you would slide under your seat or impact your head and torso as your seat collapsed. This was called seat back failure, but the seat back itself was not broken. The recline mechanism just was not strong enough to stay locked under impact loading. It did exactly what it was designed to do, which was release when enough force was applied. Crash forces were enough. Modern standards require recline mechanisms to stay locked under a much higher rearward load and prohibit designs that rely solely on friction. Positive locking mechanisms are now required. Seats are slightly heavier and the recline mechanism is more complex, and passengers stop being folded forward by their own seatback when the person behind them loaded into it during a crash. The recline mechanism was certified. The test load was just much lower than what actually happened in accidents. By the time this was updated, the failure mode had been observed in dozens of survivable crashes. It took years for the standard to catch up. The retrofit seat track adapter certified for use in aging aircraft in the 2000s. This is where the whole thing gets darkest. Airlines wanted to install modern seats in older aircraft without replacing the entire floor track system. Floor track replacement is expensive. It requires major disassembly of the cabin, so manufacturers developed adapters, a bracket that let new seats mount to old tracks, lighter and cheaper than floor replacement. These adapters were certified as a modification to the existing seat installation. The adapter was tested with the new seat. The old track was assumed to meet its original certification. What was not tested was the interaction between the adapter, the new seat, and the old track under realistic crash loads. The geometry was different. The load paths were different. The old track was designed for seats that weighed less and distributed load differently. In at least one accident, seats with certified adapters pulled out of old floor tracks during a survivable crash. The adapter did not fail. The seat did not fail. The old track failed because it was being loaded in a way it was never designed for. Post-accident investigation found that the adapter changed the load distribution enough that the old track was seeing stress concentrations it was not engineered to handle. The adapter certification tested the adapter. It did not test the entire system. Modern regulations require any modification to seat mounting systems to be tested as a complete system, including the airframe structure it attaches to. You cannot just test the new part. You have to test how the new part changes the behavior of the old parts. Airlines lost the cheap option for seat upgrades. Full floor track replacement became mandatory in many cases. And passengers stopped sitting in modern seats that were bolted to old floors with adapters that were certified in isolation. This one haunts engineers because everyone involved did their job correctly according to the standards at the time. The standards just did not require system-level testing. They required component-level testing. Aircraft are systems. Components do not fail in isolation. The final category is the bench seat configuration certified for some small commercial operators in the 2000s. Bench seats instead of individual seats, 3 people across, 1 seatbelt per person, all attached to the same seat frame, lighter than 3 individual seats, cheaper to install, certified under Part 135 rules for small commercial operators. The problem was the shared structure. If one passenger was significantly heavier than the others, the load distribution during a crash was uneven. The seat frame would twist. Seatbelts attached to a twisting frame do not restrain the way they are supposed to. In one accident involving a small charter aircraft, the bench seat frame twisted during impact, and two of the three passengers were not adequately restrained even though they were belted in. The frame was certified for the total load of three average passengers. It was not tested for what happened when those three passengers were very different sizes, and the loads were asymmetric. Modern standards prohibit bench seating in commercial operations unless each seating position has an independent load path to the aircraft structure. You can still have a bench, but each position has to be engineered as if it were a separate seat. Most operators just went to individual seats because the engineering cost was not worth it. What was lost was simplicity and cost savings for small operators. What was gained was seatbelts that actually restrained people even when the person next to them was twice their size. The bench was tested with evenly distributed dummies. Real passengers are not evenly distributed. Every one of these certifications was signed by engineers who were following the rules exactly as written. Years of incidents and injuries. People who did not make it because the thing that was supposed to hold them in place was certified for the wrong failure mode. Next time you are on an aircraft and you notice how solid the seat feels, or how the armrest does not move unless you deliberately unlatch it, remember what it replaced. Drop a comment telling me which of these shocked you most. Next time, I am breaking down features that airlines quietly removed in the last 10 years that nobody noticed were gone. Some of them you used on every flight, or used to.